Now we will discuss about the hybrid parameters of transistors and junction field effect transistor, subject of the analog electronics. So what is the hybrid parameters or H parameter model? The equivalent circuit of a transistor can be drawn using simple approximation by retaining its essential features. These equivalent circuits will aid in analyzing transistor circuits easily and rapidly. So here two-port device and network parameters. We can see this in this circuit diagram. A transistor can be treated as a two-port network. The terminal behavior of any two-port network can be specified by the terminal voltage V1 and V2 at part first and second respectively, and current I1 and I2 entering part first and second respectively as shown in this figure. So that is the circuit diagram or block diagram of the two-port network. Of these variables V1, V2, I1 and I2, two can be selected as independent variables and the remaining two can be expressed in terms of these independent variables. These lead to various two parts parameters, out of which the following three are more important. Z parameters or impedance parameters, Y parameters or admittance parameters, H parameters or hybrid parameters. So these are the three types parameters Z, Y and H. Why is the name hybrid parameters? The four parameters associated with this model are input impedance, current gain and output conductance. Since their units are completely different from each other, this set of parameters is called as a hybrid parameters. The input current I1 and output voltage V2 are takes as independent variable. The input voltage V1 and output current I2 can be written as by this equation V1 equal to H11 I1 plus H12 V2, and second also I2 equal to H21 I1 plus H22 V2. The four hybrid parameters H11, H12, H21 and H22 are defined as follow. H11 equal to V1 upon I1 with when V2 equal to 0 or equal to input impedance with output part short circuit. So this is the H11. Next, H22 equal to I2 upon V2 with I1 equal to 0 or H22 means output admittance with input part open circuit. Next, H12 equal to V1 upon V2 with I1 equal to 0 and also H12 equal to reverse voltage transfer ratio with input part open circuit. And H21 equal to I2 upon I1 with V2 equal to 0 and also H21 equal to forward current gain with output port short circuit. So these are the some hybrid parameters equations of H11, H12, H21 and H22. The dimension of H parameters. So H11 have the dimension ohm, H22 in Moho, and H12 and H21 is the dimensionless parameters. So as the dimension are not alike, they are hybrid in nature, and these parameters are called as hybrid parameters. I1 equal to 1 input and not equal to 2 or equal to output. F equal to 1 equal to forward transfer, and R equal to 1 to reverse transfer. So notations used in transistor circuits here, HIE equal to H11E equal to short circuit input impedance, and H naught E equal to H22E equal to open circuit output admittance, HRE equal to H12E equal to open circuit reverse voltage transfer ratio, and HFE equal to H21E equal to short circuit forward current gain. So these are the notations used in transistor circuits. Here the hybrid model for the two-port network. So the equation of for this hybrid model for two-port network, V1 equal to H11 I1 plus H12 V2, and also I2 current equal to H11 I11 plus H22 into V2, and also we can write these equation V1 equal to H1 I1 plus HR V2, and also I2 equal to HF I1 plus H0 V2. So these are the two hybrid equations for the two-port network. That is the two-port network hybrid model of the transistor. Next, transistor hybrid model. Consider the simple common emitter configuration of in this figure. For this configuration, the four variables are as follow. First variable input current I1 to IV base current, and second input voltage VI equal to VVE or voltage base to emitter, and third one is output current I naught equal to IC, where IC is the collector current, and fourth one is output voltage V naught equal to VCE, where VC is the voltage collected to emitter. So this is the circuit diagram for the common emitter, and also the equivalent circuit of this common emitter in this. So in this second circuit diagram, so this is the hybrid transistor models. Now, by applying KCL at the collector node in this circuit diagram, expression for H parameter for CE configuration can be obtained from above equation by let BC or IV equal to 0. H parameter for CE configuration are, if we consider VCE equal to 0 and IN and HIE equal to VDE upon IV, and also HFE equal to IC upon IV. So HFE is the ratio of collector current to base current. Now, if we consider base current equal to IV 0, in that case, HRE will be equal to VBE upon VCE, or H naught E equal to IC upon VCE from the circuit diagram. Hence, we can neglect HRE and H naught E while drawing the H parameter equivalent circuit. Such an equivalent circuit is called as the approximate hybrid equivalent circuit, which is shown in the above figures. Note that the dependent voltage source VCE has been replaced by a short circuit, and H naught E has been replaced by an open circuit. Next, hybrid parameters model for the CC configuration or common collector configuration. So in CC configuration, H parameter for CE configuration are, if we consider VEC equal to 0 and HI equal to VBE upon IV, and also HFE equal to IE upon IV. So now if we consider IV equal to 0, so HRE equal to VBE upon VEC and H naught E equal to ICE upon VEC. So these are the parameters for the common collector configuration. If these parameters are specified for a particular configuration, then suffix E, D or C are also included. For example, HFE, HIV are H parameters of common emitter and common collector amplifiers. Using two equations, the generalized model of the amplifier can be drawn as shown in this figure. So in this figure, this is the generalized model of a amplifier. Now there are various forms, and for common emitter, common base and common collector, and different value of in different configuration of the parameters. So HI is the input impedance and measure in ohm equal to VV upon IV in common emitter and equal to VE upon IV in common base, and HI also equal to VV upon IV in the common collector configuration. Next parameter HR, that is the unitless. So HR equal to VB upon VC. This is the voltage gain for the common emitter, and this will be equal VE upon VC in the common base configuration, and HR also equal to VB upon VE for the common collector configuration, and also HF, that is the unitless, or that is the current gain, and HFE equal to IC upon IV in common emitter, and HFE equal to IC upon IB in the common base configuration, and also HFE equal to IE upon IB in the common collector configuration. Next parameter is the H naught in watt. So H naught equal to common emitter ICBC, and for common base this will be equal to ICBC, and for the common collector this will be S or S naught equal to IEBE. So these are the different parameters and have the different uh, value in different configurations. So what are the merits of hybrid models? H parameters can be easily measured, and also they can be calculated from the static characteristics of transistors. Next one, manufacturer provide H parameters in their data sheets. H parameters can be used easily and conveniently in circuit analysis and their design. So these are the some merits of the hybrid models. What we have some demerits of the hybrid models also. The demerits is that the hybrid parameters suffer from a major disadvantage that they are defined only for a particular set of operating conditions. So this is the first demerits of the H parameter. Second one is the parameters of their equivalent circuit can be determined for any region of operation within the active region and are not limited by the single set of parameters provided by the specification sheets. So these are the some demerits of the H parameters. Now next one is small signal amplifier analysis. So we represent the transistor amplifier circuit in the form of a two-port network, and this two-port network represented the transistor in any one of its three configuration: common emitter, common base, and common collectors. So what is the meaning of analysis? In the process of analysis, we obtain the expression for the following parameters of an amplifier. First one is the current gain, second one input impedance, next one voltage gain, and fourth one is output resistance. So these are the some parameters of amplifier. By comparing the values of these parameters with the others, we can judge the performance of the amplifier. So some steps to follow for analysis of a transistor amplifier circuit. So first, replace the DC voltage source by a short circuit. This is the analysis of a transistor amplifier circuit. And second point is replace each of the coupling capacitor and bypass capacitors by a short circuit. And next, finally, replace the transistor by its hybrid equivalent model or remodel and proceed with the analysis. So these are the some steps to follow for analysis of a transistor amplifier circuit. Now we will discuss about the next type of transistor, that is the field effect transistors. So what is the field effect transistor or junction field effect transistor or JFET? So in field effect transistors, FET is a transistor that use an electric field to control the shape and hence the conductivity of a channel of one type of charge carriers in a semiconductor material. FET are unipolar transistor as they involve single carrier types operation. Single carriers may be holes or electrons. The concept of the FET The BJT, though it was not physically implemented until after BJT due to the limitation of semiconductor materials and the relative easy to manufacturing BJT compared to FET at the time. So FET can be majority charge carriers device in which the current is carried predominantly by majority carriers or minority charge carriers devices in which the current is mainly due to flow of minority carriers. In the FET, the device consists of an active channel through which charge carriers, electrons or holes flow from the source to drain. Source and drain terminal conductors are connected to the semiconductor through ohmic contact. So the conductivity of the channel is a function of the potential applied across the gate and source terminal. So the FET has three terminals. First one is the source terminal, and second one is the drain, and third one is the gate. So FET is the three terminal device, semiconductor device. In source S, through which the carrier enter the channel, conventionally current entering the channel at S is designated by IS. IS is the source current. Next is the terminal drain through which the carriers leave the channel. Conventionally, current entering the channel at D is designated by ID, drain current. Drain to source voltage, VDS, that is the drain to source voltage. Gate G, the terminal that modulates the channel conductivity by applying voltage to the gate. One can control the drain current. So there are comparison of symbols of BJT and FET. So in BJT there are three terminal base, emitter and collector. What in FET? Two types, N channel FET and P channel FET. So in first diagram there is the symbol of the N channel FET in which three terminals, gate, drain and source. In second symbol is the P channel FET in which also three terminal, gate, drain and source. The main difference between N channel and P channel FET is the gate, the sign of arrow in the gate. In N channel, this sign will be inside, and for P channel, this sign in gate will be outside. So this is the main difference between the N channel FET and P channel FET. So terminals of the FET, that is the gate, source, drain. All FET have source, drain and gate terminals that correspond roughly to the emitter, collector and base of the BJT. Most FET have a fourth terminal called the body, base, bulk or substrate. That is the fourth terminal. It may be body, base, bulk or substrate. This fourth terminal serves to bias the transistor into operation. So it is rare to make non-trivial use of the body terminal in circuit designs. What its presence is important when setting up the physical layout of an integrated circuit. The size of the gate length in the diagram, it is the distance between source and drain. The width is the extension of the transistor in the direction perpendicular to the cross section in the diagram. Typically, the width is much larger than the length of the gate. A gate length of 1 micrometer limits the upper frequency to about 5 gigahertz and 0.2 micrometer to about 30 gigahertz. So that is the very high frequency. So FET is also classified in first one in N channel FET and P channel FET, and also a MOSFET metal oxide field effect transistor, also classified in two types: enhancement MOSFET and second one is depletion MOSFET. And enhancement MOSFET again classified in two types: N channel E MOSFET and P channel E MOSFET. And depletion MOSFET again divided in two parts: first N channel D MOSFET and P channel D MOSFET. Here E for enhancement and D for depletion here. So systematic symbol for the junction field effect transistor JFET. First symbol for the N channel JFET and second one is the P channel JFET. So in N channel JFET gate source drain, the arrow in the gate, the direction of arrow in the gate is inside, but in P channel the direction of arrow in the gate is the outside. So that is the main difference of the schematic symbol for N channel JFET and P channel JFET. So there is also N channel JFET symbols and P channel JFET symbols. Also there is a N channel JFET offset gate symbol. So here second symbol is the for the N channel JFET offset gate symbols. Next, what is the operation of JFET or what is the working principle of the JFET? So there is the FET diagram and which is applied the DC voltage across the drain and source here also. So there is the circuit diagram which is show the operation of JFET. When neither any bias is applied to the this circuit diagram to the gate, or when BGS equal to 0, nor any voltage to the drain with respect to source, means when VDS equal to 0. In that case, the depletion region around the PN junction in this circuit diagram are of equal thickness and symmetrical. Second, when positive voltage is applied to the drain terminal D with respect to source terminal S without connecting gate terminal G to supply. So in this figure, the electron which are the majority carriers. So electrons are the majority carriers. Flow from terminal S to terminal D, whereas conventional drain current ID flow through the channel from D to source. Due to flow of this current, there is a uniform voltage drop across the channel resistance as we move from terminal drain to terminal source. This voltage drop reverse bias the diode. The gate is more negative with respect to those points in the channel which are nearer to drain than to source. Hence, depletion layers penetrate more deeply into the channel at point laying closer to D than to source. Thus, wave-shaped depletion regions are formed in this diagram figure. When BDS is applied, the size of the depletion layer formed determines the width of the channel and hence the magnitude of current ID flow through the channel. So that is the working principle of the field effect transistors. Next device is the MOSFET and metal oxide semiconductor field effect transistors. Or MOSFET is a transistor used for amplifying or switching electronic signals. So MOSFET is used for the amplifying or switching electronic signals. Although the MOSFET is a four-layer terminal device with source, gate, drain, and body terminal. So there are four total terminals in MOSFET. First one is source, second gate, third drain, and fourth one is the body. And we can also see this in this diagram of the MOSFET in that source, gate, body, and drain terminals here. The body or substrate of the MOSFET often is connected to the source terminal, making it a three-terminal device like other field effect transistors. So in this MOSFET, body terminal is connected to the source terminal to make it into three-terminal device like that FET. Because these two terminals are normally connected to each other or short circuit internally, only three terminals appears in electrical diagrams. The MOSFET is by far the most common transistor in both digital and analog circuit, though the bipolar junction transistor was at one time much more common. So in these figures, the P-channel FET circuit symbols, these are the same as the circuit symbol for N-channel device, except for direction of the arrow heads. So first symbol is for the JFET, second symbol for the depletion MOSFET, and third symbol for the enhancement MOSFET. What is the advantage over conventional transistor? So FET is the unipolar device. It means the FET operation depend on only one type of charge carriers, that may be holes or electrons. In FET voltage control device, so FET is the voltage control device in which gate voltage controls drain current. So this is the voltage control device. FET have the very high input impedance or 10 to the power 9 to 10 to the power 12 ohm. This is the impedance value of the FET input impedance, that is the very high. Next advantage of FET, source and drain are interchangeable in most. So we can interchange the source terminal and drain terminal in the FET device. And also FET is the low frequency applications. So these are the some applications of the field effect transistors. In FET, low voltage, low current operation is possible. So due to this low voltage, low current, the low power consumption here, and less noisy as compared to BJT, sorry. So less noisy as compared to BJT transistor. In FET, no minority carriers storage turn off is faster device, and FET self-limiting device. And also FET is a small in size, occupies very small space in IC, integrated circuits. Low voltage, low current operation is possible in metal oxide field effect transistors. So zero temperature drift of output is possible in this device. But there are some disadvantages of the field effect transistor. So first disadvantage is that it has a relatively low gain bandwidth product compared to a BJT. The MOSFET has a drawback of being very susceptible to overload voltage, thus requiring special handling during installation. So this is the disadvantage of the FET. Next disadvantage, the fragile insulating layers of the MOSFET between the gate and channel makes it to electrostatic damage during handling. This is not usually a problem after the device has been installed in properly designed circuits. So these are the some disadvantage of the FET, and there are some applications of field effect transistor. So the most commonly used FET as the MOSFET, the CMOS complementary metal oxide semiconductor process technology is the basis for modern digital integrated circuits. This process technology use an arrangement where the usually enhancement mode P-channel MOSFET and N-channel MOSFET are connected in series such that when one is on, the other is off state. In FET, electrons can flow in either direction through the channel. When operated in the linear mode, The naming convention of drain terminal and source terminal is somewhat arbitrary, as the devices are typically not always pulled symmetrically from source to drain. This makes FET as a suitable for switching analog signal between paths multiplexing. With this concept, one can construct a solid state mixing board. For example, a common use of the FET is an amplifier, for example, due to its large input resistance and low output resistance. It is effective as a buffer in common drain source follower configuration. So these are the some application of this field effect transistor device. Now these are two books for the this topics, and we refer to these books for cover this topics. First book is the Electronic Device and Circuit by the Millman and Halkias. Second book, Principle of Electronics by Baxi and Borse. There are some multi-choice questions. That is the very important and very interesting to clear the concept of the these topics. So question first, a JFET is similar in operation to ball. So option A, diode, option B, pentode, option C, triode, option D, tetrode. So here correct answer is pentode. So JFET is a similar in operation to pentode. Next, the transconductance of field effect transistor depend upon option A, drain supply, option B, the type of FET, option C, gate to source voltage, and option D, gate current. So correct answer here, option C, gate to source voltage, because in field effect transistor, the transconductance depend on the gate to source applied voltage. So correct answer is the option C here. Next, the voltage gain of cascade amplifier using FET is option A, product of two voltage gain, option B, equal to CD amplifier, option C, almost equal to CS amplifier. CS means common source, CD means common drain amplifier, and D one is the none of the above. So correct answer here is the option A. The voltage gain of the cascade amplifier using FET is the product of two voltage gains. Next question. A FET is a control device, whereas bipolar transistor is a control device. So option A, current and voltage. Option B, drain and gate. Option C, gate and drain. And option D, voltage and current. So correct option and correct answer here is option D, because FET is a voltage control device, and whereas bipolar transistor or BJT is the current control device. So here correct answer is option D. In FET, the drain voltage above which there is no increase in the drain current is called voltage. So option A, critical voltage. Option B, pinch of voltage. Option C, breakdown voltage. And option D, peak of voltage. So for the FET, the drain voltage above which there is no increase in the drain current. So this is called the pinch of voltage. At the pinch of voltage, there is no increase in the drain current ID in the field effect transistor. So what is the pinch of voltage? That voltage at no increase in the drain current, that is the pinch of voltage in the FET. This is the very important terms, pinch of voltage. Next, FET act as a constant current source in option A, ohmic region, option B, breakdown region, option C, pinch off region, and option D, both B and C. So in FET act as a constant current source. So correct answer is option A, in ohmic region, in which the current is constant source current in that region. That is the region is the ohmic region. So correct answer is A. Next, the gate input current of an FET is the order of option A, amperes, option B, microamperes, option C, milliamperes, option D, 100 of nanoampere. So what is the range of the gate input current of a FET? So here correct answer is the option D, 100 of nanoampere. That is the very small amounts of the currents, nanoamperes. So correct answer is the option D. Next, which of the following is the common features between FET and BJT? So here, what is the common feature between the field effect transistor and bipolar junction transistor? So first option A, difficult to bias. Option B, low voltage gain. Option C, low input impedance. And option D, current control device. So here option D is correct, current control device. And next and last questions. In the ohmic region, the FET can be used as option A, voltage variable capacitor, option B, voltage variable inductor, option C, voltage variable resistor, option D, none of the above. So in ohmic region, the FET can be used as a voltage variable resistor or VVR resistors. So thank you very much.